Yeah.
Probably, yeah. Somebody did email me that there was a white spot in the, because I was doing it off of the whiteboard instead of off of the screen.
I'm studying for my MCAT and it's crooked.
You know what? It was not a student of mine. It was some random. Okay, ladies and gentlemen, we are on chapter 14, which is acids and bases. So here we go. Some vocab. Acid is Latin for sour tasting. Alkali is Arabic for bitter. However, we had 2 native Arabic speakers in my last period, and they said, no. I have no native Latin speakers, so acid could mean sour tasting. I don't know.
That's a shame.
I'm going to use these words interchangeably. Hang with me, please. A proton is the same thing as a hydrogen ion. A hydrogen ion is a hydrogen atom that's had its electron removed. A hydronium ion is a proton in water. Get it? This would be the same thing as this in water, which would be the same thing as this. So all of these are equivalent terms. Now, there are 3 acid-base models that you need to talk about. The Arrhenius one, yes, it is the Arrhenius from that nasty equation, produced the most elemental acid-base model. Finally, he did something easy all of us can understand. This is what you learned in junior high. An acid produces a hydrogen ion, an H+, a proton, in water. A base produces a hydroxide ion, an OH- in water. This is very limited because it only applies to aqueous solutions and it only accounts for one type of base. This is most definitely a base, and it will not fit the Arrhenius scheme of things. So a few years down the road, Mr. Bronsted from Sweden and Mr. Lowry from Britain came up with a more useful type of model. They said an acid is anything that can donate a hydrogen ion, and a base is anything that can accept that hydrogen ion. Okay, so this scheme means that they must come in pairs. Now, in order to be a Bronsted-Lowry hydrogen ion acceptor, you have to have a non-bonding pair of electrons to accept the hydrogen ion. What? Oh yeah, a Lewis dot diagram. Okay, and we went with this, so let's draw the Lewis dot diagram for that really quickly. It does have a lone pair of non-bonding electrons, so it can accept a hydrogen ion, and therefore it can act as a base. All right, so my favorite reaction, A plus B yields C plus D, has been shelved for a little while. Now, here I have this. An acid, which is a proton plus an anion, and a base, in this case, the base happens to be water, yields a conjugate acid and a conjugate base. Now, we did talk about this in Chem 1, but you've slept since then, so we're going to a couple of times. We're going to revisit it. And the Bronsted-Lowry schema makes you look at what's happening on the reactant side. You need to look at the product side to figure out which you're going to name as the acid and which you're going to name as the base. Okay, so an acid is anything that can donate a hydrogen ion. Well, both of these look like they're capable of donating a hydrogen ion. They both have hydrogens. Looking on the other side, you want to see what happened in the product side, and you see that the HA on the product side has been stripped of its H. Obviously, it donated. So it donated on this side, and what is left over is the conjugate base. I like to think of these this way. First and foremost, you only find conjugates as products. I like to think about this as conjugate, meaning leftover. And whatever is left over will be the opposite of what happened on the reactant side. So, we determined that by looking at the reactants that the anion is alone, so this HA donated. So on the other side, it is the conjugate because it's a product, and it is a base because it's opposite of the acid. All right. Now, H2O served as a base in this reaction, and on the opposite side is the conjugate, and it's an acid. And you can see the difference between this and this would be the proton. Now, a conjugate acid-base pair are two substances related to each other by accepting and donating. So if you had HA and it is an acid and you wanted to know its conjugate base, that would be this. Likewise, this would be the base, this would be the conjugate acid. And if you are awake this morning, you will notice that the conjugates could also, if the reaction were going the other way, serve as a base and an acid. Ah, get it? Here's the H that it could contribute right there, and this could accept the H. Okay. Now, you're going to need to be able to do these quickly and accurately, so there will be a worksheet to follow. It will be due tomorrow. Look, due tomorrow, because I'm trying to kill you. In the following reaction, identify the acid on the left and its conjugate base on the right. Similarly, identify the base on the left and its conjugate acid on the right. So I am just going to look at this in toto and know that one of these has to be the acid, one of these has to be the base. Which one is which? They both have hydrogens, so no help there. I need to look at the other side and see what happens. HBr on the other side is Br minus. So this obviously has to be the acid because it's been stripped of its proton. What is left over would be the conjugate base because these must appear in match sets. This must be the base. How can I tell? Well, first of all, I know it has that lone pair, so it could accept an electron. It could accept a proton. And on the other side, I see the proton. So this would be the conjugate acid. Alrighty, what's the conjugate base of H2S? Well, that's asking a whole lot of you. Let's write the entire equation. H2S, what's the other reactant there? Water.
Are we just supposed to know that?
Pretty much, yeah. Almost all of this is happening in solution. All right, so I need to figure out what's going to happen here. And they tell me, this giant clue, that there will be a conjugate base of this. Therefore, this must be the acid, and then this must be the base. So on the other side, I need to ditch a proton. To ditch a proton, I would have that. Hey, that's pretty tricky. And this base must accept that proton, so it becomes...
Where have I seen that before?
Where have you
is that
seen that
called?
before? This? What is this called?
No, the HS minus.
Hydronium ion.
Okay, that's that. The I'm just going to call, I don't know, well, it would be a, I don't know,
What is
an
hyd-
HS.
What does hydronium taste like?
Yeah.
Because if it's just
Acid.
acid,
Yes.
is it strong enough to kill you?
Is it like
What
acid
are,
water?
it is acid water. That's exactly what it is. Don't be
So does it
drinking
kill
this.
you?
What are you thinking of
Well, it's
that
just
sounds
water
like
with an
that?
extra proton, so.
Well, so is deuterium, and that ain't working out well either. There's a, you know,
Does it look the same as water? Could you get
you've
fooled?
seen it. Yes, you've seen, yes.
What if we
Anytime
were drinking it and we didn't know?
you are drinking it in some small quantities all the time because your drinking water is treated with chlorine.
Oh, God.
I'm scared.
Golly. What is the conjugate acid of NO3 minus? Obviously, if it's conjugate, this must be the base. So NO3 plus H2O, HNO3 plus, well, there you go. Now, Mr. Lewis was very proud of his dot diagram, so he decided that he needed a whole set of acid and base models just for himself. So he decided that an acid is anything that could accept an electron pair, and a base is anything that donates an electron pair. So this would be a Lewis dot, a Lewis acid or base? Base, because it's going to be donating that lone pair, while this exception to the octet rule is most definitely an acid. It's acid. It's got that hole right there. Look at, there's only 6 electrons around the central atom. It's hunting some free electrons, and it found it right there. So this would be the base, this would be the Lewis dot acid. And generally on the AP exam, they're just asking you to identify, which is good for us. Okay, more vocab. Monoproduct means it is capable of donating 1 hydrogen ion. There it is. This, you will notice, is the acetate polyatomic ion. In the acid is called acetic acid. A diprotic means it is capable of donating 2 hydrogen ions, 1 at a time, which makes these problems very nice and simple. Polyprotic means that it has many hydrogen ions, or more than 2 hydrogen ions that it can donate. Phosphoric acid has 3 hydrogen ions. An oxyacid is anything with an oxygen in it. This is any acid formed by a polyatomic ion. An organic acid, of which there are many and very important players in biochemical processes, generally have a carbon in them. A polyprotic base, will accept more than 1 hydrogen ion. So look at here, this is a base, not what you thought they looked like before today. So this, PO4 minus 3, can accept 3 protons. HPO4 minus 2 can accept dose. Okay, this is like coolness. Amphiprotic or amphoteric. This is just a nice word, amphoteric. It's a molecular ion that can behave either as a Bronsted-Lowry acid or a base. Like water. Water is the famous one, and we've already seen it do just that, acted as an acid or a base. This is also amphoteric. It can give away its hydrogen ion to act as a Bronsted-Lowry acid, and it can also accept another proton, so it could act as a base. All right. Do you remember your strong acids and bases?
Yes.
Come on.
No. Class clowns in Hawaii.
Yeah. Okay, so strong acids.
H2S.
Okay. No. No.
HI.
Sober. Class. Clowns. In, I forgot the sober part, in Hawaii. Okay. Now, nitric, sulfuric, hydrochloric, perchloric, hydrobromic, hydroiodic. Clowns in Hawaii.
In Hawaii?
Or Idaho. If personally, if I'm going and I'm going to be a class clown and sober, I'm going to have this happening in Hawaii. I've been to Idaho. Okay. It's beautiful, actually, but all right, strong bases. I'm going to make this very simple for you. I'm going to use the same criteria that AP uses. They're just a cation of group 1. and the hydroxide ion. All right.
So like KOH.
Yep, NaOH, LaOH. Okay. So why do you need to know these? Because we're going to start talking about the percent dissociation or ionization of strong acids or strong bases. Okay. The percent dissociation or ionization of a strong acid or a weak base is 100%. 100%. If you had a strong acid, it will completely dissociate into the proton and its anion. If you shrunky-dunk yourself down and dove into a vat of acid, hydrochloric acid, you would find 100% of the H plus and Cl. You would find absolutely no HCl molecules.
Then you would be dissolved.
Hmm?
Then you would be dissolved.
Yes, you would be dissolved. Well, maybe. All right, and ditto for NaOH. It is completely dissociated. Now, if you don't have a strong, then you're going to have to figure out for weak acids and bases, of which there are plenty. In fact, if these are the only strongs, most everything is weak. You're going to have to figure out the percent ionization. The percent ionization for a weak acid is the molar concentration of the hydrogen ion over the molar concentration of the acid. Likewise, the percent ionization of a base will be the molar concentration of the OH minus over the strong base. Okay. So it turns out that weak acids and bases do not fully dissociate. So a weak acid will be in equilibrium with its proton and its anion, which sets you up to an equilibrium expression. Ka is the equilibrium expression for a weak acid or weak base, and it is defined as either the hydronium ion times the anion over the acid, or just the proton plus the anion over the acid. Okay, now you should be asking me, what is the Ka for a strong?
What's the Ka for strong acid?
Thank you. Remember the dissociation?
The infinity.
Yeah, it is infinity. Is this, so the Ka would be,
Error divided by 0.
uh-huh. So this would be whatever the molar concentration is divided by 0. There is none of this. So the Ka for a strong is infinity. Nobody uses that. Don't write that down. It's just kind of
I
like...
could solve
Don't
that.
write it down.
No, you just
Divided by
need to
0
know
is
that,
tangible.
that's why there is no, if you try to look up the Ka for HCl, there isn't one. Nobody publishes it because there is no equilibrium expression. It is gone to completion. Oh, I got it now. Okay. Okay. We're leaving water out of these equilibrium expressions because water is a
Liquid.
pure liquid. Okay, and very happily for you, acids dissociate one proton at a time. Wait. Here we go. So if you had phosphoric acid and you wanted to write, is phosphoric acid weak or strong?
Weak.
It's gonna be
It's going to be weak because I don't see it here. Although by the time you are graduated from college, I believe that phosphoric will be included in the strong. But that's not now. All right. It will dissociate into its proton plus this. Okay? And that will give you Ka1. Ka2 would be this dissociating into Could you write a Ka1 and Ka2 expression for each one of those? Absolutely, it would still be the products over the reactants. All righty, now,
Would there be a Ka3?
yes, there is a Ka3. I need somebody who's wide awake to tell me the relative strengths of these as, which is greater, Ka1, Ka2, or Ka3?
K1's the greatest,
Why?
because it has a higher concentration of H plus ions. Oh, I got that wrong.
Yep. But no, it is, your reason, the answer is correct. It has to do with Le Chatelier's principle. Okay,
What was that again?
never mind. We'll just leave that sitting there. All right, write the simple dissociation, ionization reaction, omitting water for each of the following acids. Okay, hydrochloric acid. No double-headed arrow because it's doing this. Acetic acid is weak. It is going to be in an equilibrium situation. For the ammonium ion, well, that seems kind of weird, but it is acting as a Bronsted-Lowry acid, and it would be that. And phosphoric acid, also weak. Okay, got it. Recalling all of these are in aqueous solutions. All right, ladies and gentlemen, in normal usage, you confuse these terms. Let's talk about them. When you're talking about a strong acid, you are not talking about a concentrated acid. Concentration means it has a high molarity. Strong means it dissociates fully. The opposite of concentrated is dilute. The opposite of strong is weak. So it is possible for you to have a strong acid like hydroiodic acid that is very dilute. It is also possible for you to have a weak formic acid. Formic acid is the acid that fire ants inject into you to preserve you until they can eat you later. It is a weak acid, but it could be very concentrated. Ew.
Is it?
Hmm?
Is it?
No, I don't think so. Otherwise, it would produce some tissue damage, and it
We're all
doesn't.
gonna die.
Yeah.
Well,
Okay. A strong acid, equilibrium far to the right. How far to the right? It has, it goes to completion. Now, what you need to know is that a strong acid or a base, okay, let's talk about acids. A strong acid, a very strong acid, produces a very weak conjugate base. The strength or weakness of a conjugate depends on its ability to attract. So here is an acid, and its conjugate base would be,
CO
all right. Now, it is weak because it has very little attraction for a hydrogen ion floating around. That's what makes it weak. If you have a weak acid, let's, okay, I want to do H2C3O2, oops, okay, acetic acid, pretend that looks right. Its conjugate would be the acetate ion. The acetate ion can attract a hydrogen because of the equilibrium going on here. All right, so you need to remember that. So a weak acid produces a strong conjugate base. Here is a pictorial of what happens in solution. If you have a strong acid and you put it in solution, 100% of it will break down. You have a weak acid, you put it in a solution, almost all of it stays the weak acid, very little of it dissociates. Here you go again. Here are your strongs. Okay, now this is kind of,
Oh, and that A is really weak, you're saying? Then that becomes a weak.
this is a weak conjugate base. This would be a
Very
strong conjugate base.
All right.
Okay. Now, if you look at this, this is a weak acid. I think intuitively, if you wanted, and you have this weak acid, it's dissociated like this, and you wanted a high hydrogen ion concentration, my guess is that you would use a more concentrated solution thinking, there will be more hydrogen ions floating around. But indeed, it doesn't work like that. Because as you increase the concentration, the number of, the percentage of ionization actually goes down. And you will be doing a mathematical, no, but you will look at that in problem form. Okay. We talked about strong bases, and now, I don't want to do this, and now I would like to talk about the auto-ionization of water. Turning page. Okay, let's say you have a lot of water particles together. Okay, they will dissociate to a very small degree and produce a H plus and an OH. And what happens is you have a Bronsted-Lowry thing going on. You have one acting as an acid and one acting as a base. I just chose them. This is going to act as an acid, and here would be its conjugate base. It was stripped of its proton. Meanwhile, another water particle acts as a base, and here is its conjugate acid. This is the amphoteric nature of water in action. You can see it acting as an acid or a base. Now, this is in equilibrium, and the equilibrium to this lies very far to the left. Most water molecules stay as a water molecule, very few ionize. However, we do need to talk about it, and we talk about yet another equilibrium expression. This is like number 5, isn't it?
17.
17 could be true. The equilibrium expression for this reaction does not include the pure liquid water as a molecule because it's a pure liquid. So the Kw for water just has the ions that are produced. The Kw for water at standard temperature, 25 degrees Celsius, is constant at this number. You should probably know this number. Kw is equal to 1 times 10 to the negative 14. Obviously, if you change temperatures, you are going to change the equilibrium constant because that's just the way it works. So this is segueing very nicely into what we're going to talk about in depth tomorrow, pH and POH. So knowing this value, you can go ahead and figure out a lot of stuff. If by chance the hydroxide and the hydrogen ion concentration are equal, as it is in pure water, then you have a neutral solution. Look, in pure water, each one of these is 1 times 10 to the negative 7. If your hydroxide ion concentration is greater than your hydrogen ion concentration, it's basic. If the opposite is true, it is acidic. At all times, this equation holds true. The equilibrium concentration is equal to the Ka, the acid equilibrium concentration, times Kb. So if you know Ka, you can figure out Kb. Got it? Because this is constant.
need a catalyst? It
Huh?
just doesn't show up in the equation. Like, does this is it auto?
The auto ionization?
Does it need a catalyst?
It is endothermic, as it says right in here. It does spontaneously